So, in this video we will continue to look at the solutions of Legendre's equation, and we have seen that this equation, Legendre equation, which is a second order linear homogeneous equation, has a polynomial solution, and a series solution if you fix your alpha as positive integer. Okay. If it is not positive integer, you can see that both the solutions are series solutions. We will have full series. Okay. y1 and y2 both are series solutions. So, we will continue to look at the solutions when the parameter alpha is a positive integer. Okay. So, we will see when n equal to 1, you can see that when n equal to 1 or rather n equal to 0. Okay. So, let me start with n equal to 0, n equal to 0, n equal to 0 if you take. So, what is the solution? This is an even integer. So, you can see that y1 of x is actually what happens when alpha equal to not n equal to alpha equal to 0, let us say. Let us take alpha equal to 0. What is alpha equal to 0? So, alpha equal to 0, so you have a 0 solution, it is 1, right. So, when alpha equal to 0, that means that corresponds to n equal to 1. Okay. So, n equal to 1 itself is 0, alpha equal to 0. So, what you get is y1 of x is 1. Okay. And then alpha equal to 2, you see that other solution y2 is series solution, is series, is a series. And if alpha equal to 1, start with 1. So, what you get is y1 is series, and y2x, this is a polynomial solution, and you can look at this y2. So, y2 when alpha equal to 1, when alpha equal to 1, so n equal to 1, you can see when you look at n equal to 1, you see that alpha equal to 1. So, what you get is all the terms involving alpha minus 1. So, when alpha equal to 1, it will be 0. So, you have y2 is actually x. Okay. Like this, you can get alpha equal to 2 and so on. In each case, y1x will be a solution. You can see that I am just writing directly when alpha equal to 2, you can see, so, okay, let us work out what is alpha equal to 2. So, alpha equal to 1, alpha equal to 2, alpha equal to 3. So, I can directly write. So, in this case it will be 1 minus 3x square, alpha equal to 3, you get y2. In this case y2 is a series, y2 of x is series. In this case y1x is series, and y2x is actually alpha equal to 3, x minus 5 by I think 8, 5 by 8 x power 8, something like this. Alpha equal to, sorry, it should be 3, 5 by 3. Okay. And alpha equal to this is a third degree polynomial, and alpha equal to 3. Okay. So, you can see that 1 minus 5 by 3. So, fine, y2 at 1. So, you can see in each case when alpha equal to 0. So, y1 at 1 equal to 1 and y2 at 1 equal to 1, but here at y1 at 1 when alpha equal to 2, if you want a polynomial, the Legendre polynomial, its value at 1, but its value is equal to 1 minus 3. So, that is going to be minus 2. Okay. So, you have to divide it with that number, so that you value y1 at 1 should be 1. Similarly, here. So, this is the polynomial solution directly from the solutions you obtained y1 and y2. Now, we will define what is the Legendre polynomial. The polynomial solutions, Legendre polynomials. So, what is the definition? So, the definition is you consider any polynomial solution, any polynomial solution p of x for alpha equal to 1. Okay, alpha equal to n. Let us say any polynomial solution p n x of the equation 1 minus x square y double dash minus 2xy dash plus alpha, I take it as n into n plus 1 y equal to 0 with Pn of 1 equal to 1 is called a Legendre polynomial. Legendre polynomial of degree n. So, you can see here. So, if you want here alpha e corresponds to 0, you want a Legendre polynomial, p naught of x will be equal to 1, whose value equal to 1. So, that is a polynomial. So, alpha equal to 1, you can see that p1 of okay. So, corresponds to alpha equal to 1. So, alpha equal to n equal to 1. If you consider p1 of x is also value x, because whose value at 1 equal to 1. But in this case alpha equal to 2, p2 of x is actually equal to, when I put y1 of 1 equal to, I am getting minus 2. So, if you multiply with 1 by minus 2 into 1 minus, that is 3x square minus 1 divided by 2. So, constant multiple of this y1 is actually a solution. So, this is whose value at 1 is equal to 1. Okay. Similarly, here p3 of x we can also write what do you get at 1 minus 5 by 3. So, 3 minus minus 2 by minus 2 by 3. So, you have 3 by 2 5 by 3 5 by. So, let me see. So, you can just you can do like this. Okay. So, I am not sure exactly this is 5 by 3 or not. So, we will see later. Like this you can get your Legendre polynomials. Okay. So, in this case so you need you first of all you have to see whether this is the solution. I am not sure whether it is 5 by 3 or 5 by 8. Okay, maybe 5 by 3 only. So, if you do this, y2 at 1 equal to 1 will give me 1 minus 5 by 3. Okay. So, this should be equal to this should be equal to minus 2 by 3. So, you divide this with this. So, you get p3 of x as 3 by 2 into 5 by 3 x cubed minus x, something like this. Okay. So, you can go on like this. So, these are your Legendre polynomials. Basically, these are solutions of this polynomial, this Legendre equation with whose value at x equal to 1 should be 1. Okay. So, you can easily see that because this is satisfying the equation, any solution, you know already that any solution yx, its general solution is the linear combination of y1x plus y2x. Okay. So, if I choose this my yx as its polynomial solution Pn of x, so where y1 is corresponds to alpha equal to n, y2 is corresponds to alpha equal to n, two linearly independent solutions. Okay. So, you have a C2 times. So, C2 times C1, C2 are arbitrary constants, and you see that this is a polynomial and this is a polynomial if n is even, this is polynomial if n is odd. Okay. So, in any case, because the Pn minus, let us choose n is even. So, if n is even, Pn is a polynomial in any case, Pn minus C1 y1 is a polynomial. Okay. But C2 y2x is a series. That means a polynomial cannot be equal to a series. So, that means C2 has to be 0 in this case. If similarly, when it is n is odd, Pn minus C2 y2 is a polynomial. So, this should be equal to C1 y1 of x, and left side is a polynomial, right hand side is a series. So, that is possible only if C1 equal to 0. So, in this case when C2 is 0, so Pn when n is even is actually constant multiple of y1 of x with some C1. Okay. Similarly, here when n is odd, this is a constant multiple of y2 of x, that is a polynomial. This is a polynomial. Okay. So, this Legendre polynomial is actually constant multiple of a polynomial solution of Legendre equations. Okay. So, how do I find this Pn's instead of looking at this series every time y1 and then you fix your value at x equal to 1 as 1 and then you decide your Pn. Instead of that, you can have you can derive a formula for Pn, okay, formula for Pn. So it is called Rodrigues formula. So Rodrigues formula. Okay, so we'll derive this today. So what is the idea? So this actually Pn of x is actually equal to some constant times that constant. You will see that 1 divided by 2 power n factorial, and n derivatives of this function x square minus 1 power n. Okay, so that is what is the formula, actual formula. So this is valid between minus 1 to 1 because these are the polynomials. Actually, it's a polynomial which is defined everywhere as a solution of Legendre equation is actually valid here. Okay, so as a polynomial it is actually valid everywhere. So you can say that is x belongs to R, but as a solution of a Legendre equation, it is this is the solution of the equation only in the range minus 1 to 1. Okay, so we will see how you derive this Rodrigues formula. So you start with consider this nth degree n derivatives, this part. So you choose so in this let u of x equal to x square minus 1 power n. So in this you take this as a function of x. You can differentiate this because it's a polynomial. Okay, so you have what if you differentiate this? U dash du by dx equal to n into x square minus 1 power n minus 1 into 2x. So this implies x square minus 1 times u dash of x equal to n times 2nx, okay, 2nx x square minus 1 power n. Okay, so this is actually your u. So I can write this as u of x. So this is what you have. So I can actually, these are u is a polynomial and these are the polynomials, product of polynomials, both left and right hand side. So you can differentiate this n plus 1 times. N plus 1 times I differentiate, okay, both sides. So to get, what do you get here? So this is the formula. This, if you apply ux vx, you differentiate n times. Okay, so this, if you write like this is the Leibniz formula. This is actually in the bracket. If I write this is a n derivatives, nc0 u n derivatives and v 0 derivatives. So that means nothing. Okay, and plus nc1 u n minus 1 derivatives, and then you have v1 derivative of x. Like this you go on like a binomial formula. So you can get ncn u times n, u times here 0. Okay, so you have n minus n, so that is 0 derivatives with u and v and derivatives of x. So this is the formula. This is the Leibniz formula, Leibniz differential rule. Okay, Leibniz rule. If you apply this here, if I differentiate both sides, this is my u, this is my v. Similarly here, x and u x, this has two functions here. Okay, so if you apply, start with x square, so n c0, n plus 1 c0, that is 1 into u square x square minus 1, and if I differentiate u n plus 1 times, then I get n plus 2 of x. Okay, so I don't write this ordinate. So plus, now you differentiate n plus 1 c1, you differentiate this, you get 2x, and this will be, I do only n times different derivative. So you have n plus 1 plus one more time you can do. So this time n plus 1 c2, n plus 1 into n divided by 2. Okay, so divide by 2. So you have 2x, now I can differentiate Okay, 2 times I am differentiating x square minus 1, so that will give you 2. So 2, and here u n and derivatives. Okay. So next time if you do n plus 1 c 3, 3 times if I differentiate x square minus 1, that will be 0, and so I do not have those other terms. Okay. So this is what happens for the left hand side. This is should be equal to, you can repeat the same thing with 2n n plus 1. So x times u n plus 1 derivatives plus 2n differentiate n plus 1 n plus 1 c 1 differentiate x once, that is 1, and you differentiate u n times. This is what you have both sides if you get. So this will give you, so if you choose this u n, let simply consider phi x as your u n of x and derivatives of x. Okay, then what happens to your phi x? So what you get is x square minus 1 phi, see 2 is the 2 derivatives are left, already n derivatives I have taken in phi, so you have n plus 2. So f phi double dash plus, and you can see that 2nx, so n square both sides will go. So this n square, and this n square, okay, so 2n squares. So if you see this, what you get is, so you can see that minus 2nx, actually 2x phi dash of x plus n into n plus 1 into phi x. So let us not do this, n plus 1 into n. So this is anyway goes. So if you see that, this is what you will get, equal to 0. So how do we see this? This is the first term, so you can easily see this here, and then u n plus 1 derivatives. You have these two terms, 2x n plus 1 and 2nx. That will, so 2n goes, and what you are left with is only this. Okay. So what you get is actually plus. Okay, this is plus. Okay, so this is plus, and now u n is n into n plus 1 and 2n into n plus 1. So when it comes this side, this if you take it to the other side, this will be minus. Okay, this is what is you get. So this is nothing but your Legendre equation. So phi double dash minus 2x phi dash, this is going to be plus n into n plus 1 phi of x equal to 0. Okay. So that means, and you see that phi, what is your phi? Phi is the n derivatives of this function u. Okay. What exactly your phi? Phi is n derivatives, so d n by dx power n of x square minus 1 power n is a polynomial solution. Polynomial solution. And if I can fix this value phi 1, what is the phi 1? What is the phi 1? If you directly calculate, you can calculate phi 1, n derivatives if you do, you can see that is going to be, so 2n plus 1. So this is a polynomial of degree 2n. U of x is actually x square minus 1 power n. This if you differentiate n times, un of x is actually 2n plus 1, right, 2n plus 1 actually, so not sure how do I put this, n into, so we will see that this is actually whose value at 1. If you directly look at this calculation, you see that, how do I see this equal to, so what we do is, here again we apply this, to get this we write x minus 1 power n, x plus 1 power n. So this I can write. Okay. Now I differentiate n times both sides. So this whole thing if I differentiate n times, okay, So, this will give me NC0, this is the as it is x minus 1 power n. You differentiate this, you will get n times. Okay. This is as it is, and you differentiate this n times. If you differentiate, you get n factorial, okay, plus NC1. So, NC1, if you do differentiate this x into n into x n minus 1, and you differentiate this n minus 1 times. Okay. So, you have a n minus 1th derivatives of x plus 1 power n, whose n minus 1 derivative. Okay. So, instead you can also do the another way. So, you differentiate, you keep this as it is. So, NC0 x plus 1 power n, and you differentiate this n times. So, you will get simply n factorial. And other things, every time you differentiate NC1, you differentiate this 1 time. So, you will get n into x minus 1 power n minus 1, and if you differentiate n, this is nth degree polynomial, if you differentiate n minus 1 times, okay, you will get some constant into some constant, but it has like that you get every time you will get. Finally, you differentiate NCN, okay. So, you will be sorry, this is the first one derivative, first derivatives, this is this will have n derivatives, will have x minus 1 term. Similarly, NCN, you do not differentiate anything here, okay, you differentiate only this part. So, you will have n factorial, and this part you keep as it is, x minus 1 power n. So, you see that first term will have x minus 1, second term will have x minus 1 square, up to last term will have x minus 1 power n. So, you see that nth derivative at 1, this is actually your phi at 1 equal to 2 power n and factorial, because all the other terms are having x minus 1, when you put x equal to 1, it will be 0. So, this is how you can see that phi 1 is actually 2n into n factorial. So, this implies my Pn of x is a polynomial solution whose value should be equal to 1. So, if I choose this phi x by phi 1, then Pn of 1 equal to phi 1 cancel, is equal to 1. So, this is exactly, you have this formula, dn by dx power n x square minus 1 power n. Okay. So, this is your Rodrigues formula for every x. Okay. As a polynomial, it is defined for all values of x, otherwise it is a solution, it is valid as a polynomial solution of Legendre equation in between minus 1 to 1. This is how you see Rodrigues formula. So, you can from this formula you can calculate your P naught, P1 and so on. Okay. So, you can easily calculate. So, x square minus 1 power n you take, fix your n, you differentiate n times. Now, what you get is this one. Okay. So, if you do this, you can see that P0 1, P0 of x is 1, P1 of x is x. From this formula you can easily see P2 of x is 3 by 2 x square minus 1 by 2, P3 of x equal to 5 by 2 x cube minus 3 by 2 x. P4, if you actually calculate, you can see that 35 by 8 x power 4 minus 15 by 4 x square plus 3 by 8. Like this you can get all your Legendre polynomial solutions. Okay. These are the solutions of the Legendre equation when alpha equal to n. So, why do we need these solutions? You have a polynomial solution when you fix the parameter alpha equal to n. Why do we study these polynomials, Legendre polynomials? Because these are the polynomials have certain properties, very important properties. These are actually, they are orthogonal to each other. That means these polynomials P0, P1, if you integrate, you take P0 and so let us say Pn of x and Pm of x, the dot product of this. So, simple as a vector dot product, here you take the functions dot product is between minus 1 to 1 dx as a solutions of this Legendre's equation, Legendre polynomials, whose dot product, okay, this Pn dot Pm. Okay. So, dot product you can write like this. Okay. if I differentiate, so the dot product you can write like this. If you write, this is the dot product of the polynomial, okay, dot product of p and pm. So this is actually, you will see that 0 if m is not equal to n. When they are different, they are actually orthogonal to each other. So if it is same, if m equal to n, then you have some number, okay. So that you will see that is actually 2 divided by 2n plus 1. So why do we need this? When you study partial differential equations in higher dimensions, you convert this, you use, instead of, you work with spherical coordinates instead of Cartesian coordinates, you convert the Laplace equation in terms of spherical coordinates. It becomes this Legendre equation you need. That is where if you actually solve the Legendre equation, you get the polynomial solutions you may have to use, and then there, to get the constants, you have to use this dot product, this orthogonal property. This is called orthogonal property, orthogonal property of Legendre polynomials. There are many properties for these functions. So we give the main important thing is this, okay. If they are different, 0, otherwise it is 2 divided by 2n plus 1 as fixed number, okay, pn square, and m equal to n, integral pn square dx value is this. So we will show this property. This is the important property you can show. There are other very important properties, but you need we need only this or some important, we will see them as an exercise, okay. Property 1 is this. So how do I know that? So Pnx satisfying the differential equation of a Legendre equation, okay. So 1 minus x square times plus, not plus, minus 2x Pn dash of x plus, this is corresponds to n into n plus 1 into Pnx equal to 0, because Pn is satisfying that, okay. Then Pmx is satisfying the other equation, Pm dash of x, Pm double dash of x, this Pm dash of x. This is the different equation with n equal to m. So n into m plus 1, which is Pm of x equal to 0. What I do is I multiply this equation with Pm of x, and I multiply this equation with Pn of x, both sides, okay. So if I do this, this I multiply with Pm of x, which is equal to 0. This I multiply with Pn of x, which is equal to 0, okay. And then you take the difference. When n is not equal to m, you take the difference. When you take the difference, what you get is n into n plus 1 minus m into m plus 1, the last terms, into Pn Pm, okay. This is equal to, what is the difference here? Pn Pm. So what you get is 1 minus x square into Pn double dash of x into Pm of x minus 2x Pn dash into Pm minus 1 minus x square Pm double dash Pn of x minus minus plus, okay, 2x Pn Pm dash, okay, Pm dash of x into Pn. This is what you have, okay. So now you try to integrate both sides. I integrate, this is a constant which is non-zero because n is not equal to m. If you integrate from minus 1 to 1 dx, both sides, you try to integrate from minus 1 to 1, okay. This is your function dx. What you see is, so I can rewrite this as minus 1 to 1, 1 minus x square. First two terms I can write 1 minus x square Pn dash whole dash. What is this one? What is this one? 1 minus x square Pn double dash, that is the first term, and minus 2x Pn dash this into with Pm. This is my first term, first two terms, first this row, first two terms is this, minus second two terms also you can write it the same way. So, 1 minus x square Pm dash whole dash into Pn dx. Now, one you integration by parts, one integral you integrate by parts. So, this is your full integrand. The first term you do the integration by parts. So, you will get 1 minus x square Pn dash Pm with the limits minus, so integral minus 1 to 1, 1 minus x square Pn dash Pm dash. Okay. And you do the same with other things. So, minus 1 minus x square Pm dash Pn, this is from minus 1 to 1, and the minus minus plus you get minus 1 to 1, 1 minus x square Pm dash and Pn dash. You see that these are same integrals with plus or minus, they gets cancelled, and this is what is the remaining. So, when you put x equal to plus or minus 1, this term will be 0 and this term also will be 0. So, this together it becomes 0. This is what happens when n is not equal to m. When n equal to m, okay, if n equal to m, so you cannot use the same procedure above. What we do is, so we know we use the Rodrigues formula Pn of x, n equal to m, we consider Pn of x is, you have seen that 2 power n n factorial into that n derivatives of dn by dx power n of x square minus 1 power n. Okay. So, you call this some u. Okay. So, we can write like 1 by 2 power n n factorial u of x, okay, for which you have n derivatives. You can write like this, n derivatives for u is this function. Okay. So, if you write like this, you want to know what is this Pn Pm. So, that means Pn square of x dx. So, this is equal to minus 1 to 1. You can directly calculate using this formula. You have 1 by 2 power n n factorial square into un of x into un of x 2 times dx. Okay. So, this is just a constant, you can take it out, minus 1 to 1. So, let us evaluate this integral. This integral, if you evaluate n derivatives of x, n derivatives of x dx, you just do the integration by parts, what happens? U n minus 1 of x. Okay, this, let us say this I integrated. Okay. I bring n derivatives here. Okay. So, what is the integration by parts? First you write un minus 1, this is the derivative of this is this. Okay. So, this into un of x, and you have minus 1 to 1 minus, what exactly I did is I take one derivative, bring it to here. Okay. So, one derivative you bring here to here. So, you have, when you do that, you have un minus 1 of x, and then you have un plus 1 of x dx. Okay. And you know that un minus 1, you see that what is un minus 1? This is un minus, so n derivatives of this is this, which is nth degree polynomial. Okay. Or rather n derivatives of x square minus 1 power n. This is the ux is nth degree polynomial in x square. Okay. And when you differentiate n minus 1 times, you will still have x square minus 1. When you put minus 1 plus 1, that will be 0. Okay. So, what you have, when you bring one derivative, you have minus 1 to 1 this. Okay. You integrate one more time, this will become plus. Okay. So, you do the same thing, same technique. So, if you do the same technique, so what you get is you bring one more derivative here to here. So, you have un minus 2 of x, un plus 1 of x, this is from minus 1 to 1. Again, n minus 2 derivatives of ux will have x square minus 1. So, this term also will be 0, minus minus now plus minus 1 to 1 un minus 2 of x. I brought one derivative here. So, you have un plus 2 of x dx. Like this you can go on. Okay. So, every time once it is plus, first one derivative you bring it plus minus, and two derivatives you bring it is minus plus. So, it is like 1 minus 1 square. Two derivatives when I bring, I have a minus 1 comes out 2 times. Like that you can go on. So, you finally end up, this is same as minus 1 power n. I take all the derivatives, n derivatives here to here. So, that is 0 derivatives here now, and you have n plus n, that is 2n derivatives of x dx. What is u? U is this. 2n derivatives means you simply have, it is a polynomial of degree 2n, x power 2n plus something something, right. This is the polynomial u of x. If you differentiate 2n times, what you get is simply 2n factorial. So, what I get is this one as minus 1 power n 2n factorial, okay, and then integral minus 1 to 1. What is ux? X square minus 1 power n dx. Okay. So, this minus 1 power n, if you take it inside, 2n factorial minus 1 to 1, 1 minus x square power n dx. Now, this you can evaluate in many ways. One way is minus 1 to 1, 1 minus x square power n dx. If you put x equal to sin theta, what happens here is 0, x equal to minus 1, this becomes x equal to sin theta. If you put 1 minus cos square, 1 minus sin square theta is cos square theta, cos 2n, okay, cos 1 minus sin square theta cos square cos 2n theta, dx is cos theta t theta. So, cos power 2n plus 1 theta d theta. Okay, that is what you have. So, what is your this one minus pi by 2 to pi by 2. So, that is because this is minus pi by 2 to pi by 2, and x is minus 1, theta is minus pi by 2, and theta is x equal to 1, sin theta is pi by 2. So, because this is a even function of theta, so you can have 2 times 0 to pi by 2 cos 2n plus 1 theta d theta. So, if you know the formula for this, you can apply directly, which is going to be 2n into n factorial square divided by 2n plus 1 factorial. So, this is what is the formula. Okay. This is the formula for this integral. This is one way. Another way is you can see that 1 minus 1 to 1, 1 minus x square over n dx is actually, this is again even function. So, you have 2 times 0 to 1, 1 minus x square power n dx. So, this is actually, if you replace x square with t, so what you get is 0 to 1, 1 minus t power n, okay, into t power minus half dt. So, this you can write like 2 times integral 0 to 1, 1 minus t power n plus 1 minus 1 as n, t power minus half as 1 minus half dt. This is exactly your beta function. So, this is actually 2 times beta of half and n plus 1. This is 2 times gamma half gamma n plus 1 divided by gamma n plus 1 plus half. If you use that formula, you get similar thing. So, you expand these gammas, gamma half is root pi, and this you use the formula gamma n plus 1 is actually equal to gamma alpha plus 1 is as gamma alpha into gamma alpha. If you use this formula and expand these gammas, you will see exactly the same thing. So, that I leave it in exercise. So, if you use that, so what you end up is finally you have 2n factorial into 2 into 2n n factorial square divided by 2n plus 1 factorial. So, this is exactly 2 divided by 2n plus 1 into 2n n factorial square. This is what is this integral if you substitute here. So, you go back and substitute, what you see is integral minus 1 to 1 p n square x dx is exactly 2 divided by 2n plus 1, because 1 divided by 2n factorial square you have now. Okay. So, when you square it, so you have this square, so that cancels with this. Okay. So, you are left with this is what you have, n is running from, n is anything from 1, 2, 3 onwards, even plus or minus 1. Okay. So, you can say n belongs to z. Okay. So, this is what you have. So, this is the important property, it is called orthogonal property of Legendre polynomials we have seen in this video. So, we will see some more properties, and maybe in next class what we see is we will see in a different way, different formula as a polynomial expression, as a sum, finite sum for the polynomial, Legendre polynomial p n x. So, that normally you can see in you can directly derive from the polynomial solution y1x or y2x, from which you can directly get your p n of x by just fixing nth term. Okay, by choosing in a different way, we will try to get the formula for p n in a different way. Okay, so that we will see in the next video.